This is a methodological and mathematical walkthrough of arXiv 26.03.23398, graph energy matching. The paper asks whether discrete energy-based models can finally match diffusion-level graph generation quality while keeping compositional inference advantages. In molecules and materials, we need models that generate valid graphs and also let us impose constraints at inference time. Diffusion models sample well, but represent distributions implicitly through noisy trajectories. Classical discrete energy models are compositional, but often hard to sample and prone to bad local minima. GEM combines both worlds. It learns a permutation-invariant scalar potential over clean graphs, then uses that same potential for fast transport from noise and local refinement near the data manifold. So one model defines both relative likelihood and generation dynamics. The conceptual anchor is the JKO perspective. Instead of simulating continuous dynamics directly in discrete graph space, the method builds a sequence of discrete distributions connected by optimization-inspired map updates. That gives a principled bridge from transport theory to practical graph proposals. In the transport-aligned regime, epsilon goes to 0, making proposals nearly deterministic and greedy. The model reads energy gradients over node and edge embeddings, then proposes edits that reduce energy quickly. This phase is about coarse relocation from noise toward plausible graphs. After entering the high likelihood band, GEM switches to epsilon greater than 0. Now proposals are stochastic and local, then filtered by a Metropolis-Hastings-style acceptance rule. This mixing regime improves coverage and avoids mode collapse around a few graph basins. The schedule between transport and mixing is critical. GEM uses initialization choices and proposal schedules that first prioritize fast movement, then exploration fidelity. This is where many older graph EBM pipelines fail. They mix too early or stay greedy too long. Training uses coupled minibatches between noise and data, with interpolation that teaches the energy field to rank clean graphs correctly and shape useful gradients away from the manifold. The objective family includes matching terms and a contrastive view in the appendix. The practical takeaway is stable gradients for both global transport and local refinement. On unconditional molecular generation, GEM is competitive with or better than leading discrete diffusion baselines across validity, uniqueness, novelty, and distributional metrics like FCD. The paper reports especially strong final quality behavior when compute budget is not tiny. That matters in practical discovery settings where sample quality dominates latency. Because GEM models relative likelihood directly on clean graphs, it supports property-constrained generation naturally. The paper evaluates conditions like log P, log S, QED, and TPS and shows strong constrained validity and uniqueness. This is a major advantage over methods that must guide through noisy intermediate states. An especially interesting capability is geodesic-style interpolation between graphs under the learned energy geometry. These paths are evaluated for validity along trajectories, not just endpoint quality. So GEM is not only a generator, but also a geometry-aware exploration tool. The energy trajectory plots clarify the switch mechanism. Transport rapidly drops energy from noise-like states, while mixing stabilizes and explores locally. The annealed switch outperforms fixed-temperature alternatives in balancing speed and final fidelity. The discussion is honest about compute. Like many energy-based methods, gradient-based generation can have a 2 to 3 times overhead relative to very fast denoisers. The paper argues that compositional control and strong final quality can justify that cost in high-value scientific use cases. The appendix provides important implementation depth, permutation-invariant parameterization, transport map reduction details, and practical proposal mechanics. These details are critical if you want to reproduce the method faithfully rather than only copy headline ideas. Baseline analysis distinguishes conceptual families carefully, including graph EBM, VFM, and DFOG-style approaches. That framing helps explain why GEM gains are not just from larger models, but from sampler design plus energy geometry. For conditional generation, the paper also studies noise-conditioned versus uniform noise property regressors. Those choices affect guidance reliability especially away from clean data states. Reported hyperparameter tables make this comparison operational rather than anecdotal. The wall clock section on modern hardware shows a familiar curve. Some baselines improve quickly early, while GEM catches up and often exceeds final quality with more steps. So deployment choice depends on whether your objective is earliest acceptable output or highest eventual quality under constraints. A useful robustness study examines property regressor error across denoising time. This matters because conditional generation quality depends on regressor reliability off manifold. Results support the paper's argument that guidance design and noise exposure are first-class design variables. Main limitations remain. Sampling still requires iterative gradient-aware proposals, calibration quality can depend on objective tuning, and scaling to larger graph domains needs further study. But GEM narrows a long-standing gap between compositional energy models and high-fidelity graph generators. Final takeaway: graph energy matching offers a principled recipe for discrete graph generation with strong quality and compositional inference. Its key contribution is not only a better score table, but a unified energy geometry that supports transport, mixing, and controllable generation in one framework. If your workflow needs both fidelity and constraint-aware sampling, this is an important paper to know.